Hello guys, it's Mikel from Boxite here, and in today's video I will show you how to create this snowball simulation inside of Houdini using MPM solver. Throughout this video you will learn how to create realistic snow simulation using MPM solver. You will also learn a few tricks on how to bake your simulation properly to save disk space, and also you will learn how to create secondary simulations to add extra detail to your simulation. Apart from that, we will be also covering how to render and composite this shot. And if you guys like this tutorial, let us know in the comments so we can bring more about MPM in the future. For more Houdini courses and tutorials, visit boxite.com. Okay, so let's start by creating our snowball. For that, we'll need a sphere, and this is really big, so let's change this to 0.08, so it's 8 centimeters, and let's increase our rows and the columns so we have more geometry to work with. Now let's add a mountain so we can have more detail on our sphere. This shape is not really nice, so let's play around a bit with the values, maybe an amplitude of 0.2, let's put 0.2. Maybe we want smaller element size. Maybe let's do 2 mountains. So I will add a bigger element size with more strain, something like this. And now let's add another mountain. And this one will be less strength, maybe 0.1. And the element size will be way smaller, maybe 0.01. Yeah, like this. So we have a bit more detail on our snowball. Now let's preview our geometry by pressing W, and let's drop a transform, and let's place our snowball where we want to start. So I want it to be more or less around here. Maybe I can go to the side view pressing 4 and move my snowballs something around here, because I want to hit this part on the helmet. So maybe we can put it a bit more backwards. Yeah, I think like this works. So now we can just drop a null and call it snowball geo. Okay, so now we can start adjusting our MPM solver. So let's drop a MPM configure, and it will create all of these nodes for us, but we don't really need these two. And we can connect our snowball to the MPM source. We can connect our helmet to the collider. Maybe we can move this around. Let's preview this. And right away we can see that we have some problems with the helmet, and also we don't see our sphere. That's because we have to change our particle separation, and this will adjust both particles and volumes. But in case you want to have both of them separated, you can just activate this voxel size tab, and you will have the particles here and here the voxels. But in my case I will keep everything here, so I know my resolution will be 0.0003, but to preview faster I will multiply by 2.5, so now we have 0.00075, and now we can see that our snowball is here, but we can see that our helmet geometry, it's not working properly. That's because our helmet has some holes and the BDB is not calculating this properly. So to fix this, we have to enter inside our MPM collider. So let's right click and allow editing of context. Now let's go inside, and the same with this BDB collider. So let's allow editing of context and go inside. Okay, now here we have a lot of nodes, but we usually have to focus on this BDB from polygons here, and we just have to activate these preserve holes. So now we can see that this is working better, but we still have some problems here on the eyes. So let's go back once, and let's create here a BDB reshape SDF, and this will fix our helmet. As you can see, this is making our helmet much better. Now we can go back, and we don't really need to touch this anymore. Okay, so now let's adjust our values on the MPM source, and we can see here that right away we have our material preset set to snow. We have a lot of materials here, but we will just keep on the snow. And here on the velocities, we can see that we have to move towards the -x. So let's put here minus, and a value of 8 or value of 9 works nice for this simulation. So you can just play around, but for me, value of -9 works fine. And now let's go here to our MPM solver. and let's put less time scale so it's slow down, and let's do a quick flipbook here just to see what we have here. Okay, so we can see on our flipbook that the simulation is starting to work, but we don't really have breakings and the snowball is sticking to the helmet. So let's adjust that. Okay, so to make our snowball to stick to our helmet, let's change some values here in the MPM collider as the friction and the stick. So let's put, for example, 0.4 friction, and the sticky we can put 0.3. Let's do another quick playtest. Okay, so now we can see that our snowball is sticking to the helmet, but there is no breakup at all. So we will have to adjust a few values on the MPM source in order to get better breakups. We can change our critical stretch. What this critical stretch does is when you have a higher value, you will have less breakup, and when you have lower value, your points will break up more and you will have less chunky parts of snow. So let's use 0.006 for example. We can also increase the stiffness, and let's also decrease our volume preservation so we have a bit more breakup, and maybe we want to increase a bit more this velocity value. So let's do another flipbook, and now we can see that we have a bit more of breakup, but it's still not enough. So let's maybe adjust the position of our snowball, and let's change some values also. So I can see that maybe here on our snowball is hitting this part and is not letting it go through. So let's move it a bit more. Maybe we want this to move here so we can hit this part of the helmet and then the snow can go through it. Maybe duplicate this by 2 so we have 0003, and maybe we can decrease this critical stretch so we have a bit more of breakup. I think we can try a new playblast like this. Okay, so now we can see that this is working much better. We have more breakup, and right now the only thing that I want to change is that our chunks are a bit the same size. So let's make maybe a mask, and we can make our snowball to break depending on that mask. Okay, so to create the noise, let's add a attribute triangle. You can make this with attribute bob, but for these shortcuts I like to use attribute triangle. So let's create our code. Let's do add ct equals, then a float value, then we can add our noise, we add our position, and I want this noise to be 30 on the strength, then I want 5 octaves, 0.5 of roughness, and let's put our frequency to 1. So now we close this and we have this. So now we have to add a absolute values. So we put here abs and we add another close here. So now we have these lines, and now I want to fit these values to have more white and more black parts, and I don't really want these gray ones. So let's add a fit range here, and we want to fit these the values from that goes from 0 to 0.5. I want them to be 0 and 1. And now we can close this, and we can see that we have more white and more black values here. And what we are going to do with these values is to multiply our stiffness. The stiffness basically it's going to take our white parts and make these parts harder, so our points will stay together, and it will take these black parts and it will make these points to break more. So we will have more difference between the chunks, because for example here our snowball will break a lot, but here we will maintain the shape more. So in order to multiply this value, we can see here, if we put our mouse on this, that the parameter is called E. So let's add here another quick vex line. So we want our E parameter to be multiply equal to our CDX, because we want our black and white values. But now let's fit this also. So fit 0 to 1, because this is 0 to 1 values as we have here. So fit 0, 1. And then I want the values with black parts, so the values with 0, I want to multiply my stiffness by 0.1, and then my weight values, I want to multiply them by 5. So now let's run another flipbook. And before doing our flipbook, let's visualize this JP value, and we can go here. So let's make this to be our sphere purple. So maybe 35 works. And what this value is going to show us, it's the breaking points of our snowball. So this purple value means that our snowball is not breaking, and once it hits our helmet, it will start to change its color, showing what parts are breaking more and what parts are breaking less. So now let's run our flipbook. Now on this flipbook, we can see that these parts that maintain on purple are our big chunks. And as we can see here, we have more variation now. And we can see that these red values are the points that break more. So we can see that there is a few points here. And yeah, I think we have mostly all of our simulation ready. Now we just have to do a couple of things. Okay, so first of all, let's start by disabling our ground plane, because we're not going to be using it for the simulation, like this on the MPM solver. Now let's preview our helmet geometry, and let's go to our MPM container. Let's put our Houdini onto manual mode. And now if we press enter on the viewport, we can adjust our bounding box. Now let's see, I know that my simulation will be going mostly to the left, so maybe I can put this part more close to the helmet. Let's move this a bit more, and maybe this one, something around here. Also, the bottom part maybe can be something around here, and we can get this one closer to our snowball. I think something like this works, so let's press escape again, and now we can go back to our auto update. And now if we go here to our MPM container, we can press here into boundaries, and let's change this from open to delete. So now we can see our bounding box, and what this delete will make is to delete all the particles that go through our bounding box. So let's say if our snowball hits here and falls down, once it reaches this part of our bounding box, all of those particles will be deleted, and that will save us a lot of space when baking, and also we'll have more performance on the viewport. And now I think we're pretty much ready to bake. Let's just delete this multiply here, so we can have back our final resolution. I don't think we have change anything more from these values. We have our noise. The collider is working well. So yeah, now I think we are pretty much ready to bake our simulation. But before baking our simulation, I want to show you a few notes that will help you baking your particle simulations mostly. So let's start by deleting some attributes with attribute delete. And I mostly want to keep the position, the velocity, the p-scale, and maybe this JP value also. So we can use it later as masks to select some particles for our secondary simulation. And I also want the ID. Now we can delete non-selected, and we have here a more clean geometry, but we can do a few more things. Let's drop a attribute promote node, and let's promote our p-scale from points to detail. So if we open here our geometry spreadsheet and we go to our points attributes, let's go here on the attribute delete, we can see that all of our points have the same p-scale. So what we are doing with this attribute promote, it's instead of saving the p-scale into each point, which is a lot of data, we can just save this on a detail attribute and just save the p-scales in one general attribute instead of on all of our points. And this will save a lot of disk space also. But we can further compress this. Let's drop a attribute cast, and let's cast our velocities, which is b, into 16-bit float. And finally, the best node of this compressing is convert BDB points. So with this convert BDB points, we're going to pack our points into voxels, and then once we bake our simulation, we can extract our points back from those voxels, and basically we'll just have to bake a lot of less points than baking all of our original points. So let's change these points per voxel to 32, and we can change our position compression to 8-bit fixed points, and we can see here that we're going from 11 million points to only 30,000 points, which is way less than those 11 million points that we have before. So now we are ready to finally bake our simulation. So let's drop a file cache. And let's change this name, for example, to Snowball Simulation. Now we can delete the base name and keep only the $S. Just select our folder, and let's just save only 120 frames. It's enough, I think. So yeah, I see you guys once this is baked. Okay, so we finally bake our simulation. We can see here that this is working properly. We have all of our points working, and we can see that they are being deleted when they touch our bounding box. So now let's get back our attributes into our points. So let's start by adding a convert BDB points, and let's change this from packed points to extract points from BDB points. So now we have back our 11 million points that we had on our original simulation. Now let's also get back our P scale. So let's drop a attribute promote, and let's change our P scale from detail to points. So now we have back our P scale on all of our points. Okay, so now that we have all of our attributes back, let's drop a blast, and let's go some frames farther, maybe 72, maybe 48. Yeah, this is fine. And we're gonna use that attribute called JB that we used before to visualize the breakup, to take only the big parts of our simulation. So if we preview this blast and we write expression here at JB, which is our value, and we know that our purple parts were around 35. So let's put to be values higher than maybe 50, and let's run this into points. So now we can see that our big chunks are not anymore here, so we have to delete non-selected, and here we have all of our big chunks. Maybe we can play around with this value and maybe increase it maybe to 20 to have a bit more points, but you can see that we start getting some small ones here, so I think a value of 50, it's fine. And yeah, let's keep it like this. So now let's create a mesh from all of these particles here. So I'm gonna drop here a BDB from particles. I'm not gonna link it for now here on the node. BDB from particles. And before linking this to our blast, we have to change the voxel size, which is really important. So let's go back to the first frame and let's preview our MPM solver for a second. And now if we open our geometry spreadsheet and go into the detail attributes, we can see these detail attributes called dx. And it's really important to you to check this value all the times that you want to mesh your MPM simulation, because we have to make our voxel size depend on this value and add a few more that I will show you now. So let's go, we can go back to our BDB from polygons, and as we have seen, our dx value is 0.0006, and now we have to divide this by 2 and divide this by our minimum radius in voxels, which is 1.5, but I recommend you to put a bit more, so let's put 1.51, and now we have this value, which is the correct one to shape our particles. So now let's link this to the BDB from particles, and now we can see that our snowball is converted to a volume. Okay, so now that we have our volume, let's drop a BDB smooth so we can get a more smooth result here. Let's also add a BDB reshape SDF, and let's put this in a road, and maybe let's erode it by only 0.5. It's nice, so we have our snowball a bit more smaller and more compact. And now let's convert this into a mesh. So let's drop a convert BDB node. We can convert this into a polygon soup, and maybe we can put a bit of adaptivity so we have a bit less of polygons, something around here, because as you can see, the snowball is not changing that much, and we are going from 800,000 points to roughly 200,000, which is a lot of less points to work with. So now that we have our points converted to a mesh, we can just drop a null and call it out chunks. And now if we go a few frames further, let's say 48, we can see that all of our chunks are meshed properly and look really smooth and nice. And now, before starting with our secondary simulation, let's do a few more things here. So I want to add a time shift node, and I know that my last frame is 120, so I'm gonna stop this in 120. And as you can see, we are left with this part on the helmet, which I want to file cache it, and you will see later why. And I also want to file cache all my animated mesh, so let's drop here 2 file caches, one here and one here. I can connect my file cache to the time shift and check this time dependent cache because we only want one frame. I can change this to $OS, and I will rename this to helmet chunk. And we can save this to disk. And now I will connect my output here from my null, and I will do the same thing. So $OS, and this is not a simulation, so we can uncheck this. And I want to save my 120 frames, and I'm gonna rename this mesh chunks. Also, something important, whenever you are file caching something that is not a simulation, you can always click save to disk in background instead of save to disk, because with this save to disk in background, you will use all of your CPU cores and you will bake more frames at the same time. So instead of baking, let's say, 1 frame at a time, you can be simulating 5 or 8 frames at a time depending on your CPU. Okay, so now that I have my file cache ready, I have here my helmet chunk and I have here my animated chunks. Let's go and add a few nodes here to make this less detailed and bigger, and you will see later why I'm doing all of this. So let's start with the helmet chunk, and let's add a pick node, and I want to pick this by, let's say, 0.003. I think this is fine. And then I can do a BDB from polygons, so BDB from polygons, and I want this to be slower, let's say like this. Yeah, something like this work. We don't really need super high quality BDB. And here on my mesh chunks, I want to do the same thing, but I want to keep a bit more my details. So let's do a peak node, and instead of 0.003, let's do 0.001. So just a little bit, and let's do a BDB from polygons also, BDB from polygons, and instead of 0.005, let's do 0.001 also. So yeah, something like this, it's fine. And now we can add 2 more file caches. So 1 file cache here, another file cache here, and let's do the same thing. So delete $OS, this is not time dependent, and let's call this helmet chunk BDB, and the same thing here. So delete this $OS, this is not a simulation. We need 120 frames, and let's call this mesh chunks BDB. And as I mentioned before, we can save the disk in background on this one to use all the power of our CPU to bake more frames at a time. So now that we have our file cache ready here also, let's drop a few nulls. So let's drop a null here and another one here, and let's call this out mesh chunks, and this one will be out helmet chunks. So like this. And now we are ready to start our secondary simulation. So to start with our secondary simulation, let's duplicate this blast node and let's preview this. And I want to change these expressions here. Now I want values higher than 100, for example, to not be selected. And this would be our starting points for our simulation. And now let's copy our helmet chunk here and let's reference it here like this. And as we can see, if we go to our last frame, which is 120, we can see that we have here these points all the time. And when we make our top network, these points will be sourcing points continuously, and we don't really want that. So that's why we created this proxy geometry. So now we're gonna just create a group node. We can put this into points and call this delete. And let's activate our bounding regions and use bounding volume. And now we can see that we are selecting a few points here, but we really need to cover all of this, so we can increase our isosurface a bit, something like this. Yeah, something like this works. So now we can drop a blast node and we can blast our delete. So now we can see that we have our points which we will use to emit particles without that part on the helmet. Now let's add a attribute triangle and let's change our velocity values, because as you can remember, we put our time scale to 0.1, and in order to make our velocities to match that time scale, we have to multiply our velocities by that number. So if we preview our velocities now, we can see that they are super big, but now we can use to b at b multiplied equal by 0.1, which is our timescale. We can see that we have our velocities normalized and they are matching the real velocity of our particles. Okay, so now I want to randomize my velocities a bit, so our pop simulation is not super linear and it's more random. So let's unpreview our velocities and let's create a attribute bob here. We can call this noise b, and let's preview and let's go inside. So now inside of our attribute bob, we want a anti-aliased noise and we want to add this noise to our original velocity. So here in my noise, I want it to be a 4D 3D noise, and for our 4D value, we will use our time. So let's add a vector to vector 4 and let's put our position on the first input and let's put our time as our fourth component. So now we can put this into our position for our noise and we can add this to our velocities. So like this, we can now preview our velocities and we can see that this is changing our velocities. So now here on my noise, I want my time to be 2 times faster. So my noise will be changing faster. Maybe I want to add a bit more of roughness and I don't really need 8 octaves. So let's go with 3, which is enough. So with these few nodes, we have a really nice noise for our pop simulation, but I really want to randomize it a bit more. So before randomizing my noise a bit more, let's add a normalize. So we can have our velocities normalized with values from 0 to 1. And let's multiply our result by a few things. So let's drop a multiply. And I want to multiply this by the length of my velocity. So let's drop a length here and we can multiply it by this, but we can further randomize this by dropping a random from our PGNAM and let's fit range this. And I want my destination mean to be 0.9. So we only randomize the values in between 0.9 and 1. There is not a lot of change, but yeah, it's very little change that will randomize the velocities a bit more. So now we can go back and let's preview the velocities. Okay, so now what I want to do is to create a few more particles that will follow our velocities. So if I check here our velocities, you can see that we have this cool shape, and I want the new particles to follow this. So let's start by adding a attribute triangle, and you will see why I'm creating this. But for now, let's do the code, which is add replicate equals, and then clamp length of our velocity, and I want to multiply this by 0.1 and 1, and then I'm going to create here a attribute which can be called max PTS, and with this value we can control how much points we are creating. And now if we click this, we have here the max PTS, so we can leave this maybe at 1 for now, and let's create here a point replicate. Here with the point replicate, we can set this to 1. I want to keep the input geometry, and here you can see we can generate these points from an attribute. So as we said here, our attribute is called replicate. So we can connect this here, and now we can connect this here. And we can see that we are adding a few points, but we don't really see much happening. And that's because we have to tweak a bit this shape. So here, instead of box, I want to put cylinder. Let's change the uniform scale to 0.05. Let's put these velocity threads to ignore our geometry scale. And now we want to divide this velocity scale by our FPS, and this will make the particles to follow these velocity lines, as you can see. And now here on the attribute triangle, we can change this maybe to 5, so we can have a few more points. So now if we preview this, we can see that this is working on all the frames, so that's cool. And we can further noise this a bit more. We can add a attribute noise like this, and instead of the CD, we can noise our position, and I want my range values to be 0 center, and let's put less amplitude, so maybe 0.01. Yes, now we can see that this is back on its place. And here on the noise type, let's use the fast noise, and let's also decrease the element size to maybe 0.025. And as you can see here, if I do this, you can see that we are noising this so much, and this is really cool. Maybe if you want, we can keep it on 0.02, so it's not maybe too much noisy. Yeah, I think 0.02 for now works. And now with this, we can add our pop network to create our new particles. So let's go to the frame 1, and we can preview our popnet. And for now, I'm going to use 3 substeps, and let's go inside. So now inside our pop network, I want to delete this, and I want to move this a bit around, and we can start by adding our forces first. So let's add a pop drag, which I'm gonna leave as it is, and I'm gonna add a pop force, and on the pop force I want an amplitude of 0.1, so it's really small, maybe 0.15 on the surface size, and maybe a bit more of roughness, and maybe a tiny bit of wind like this, 0.2, I think that works. Now on our source, we want to source with all of our points, and on the birth tab, I want to change my life to 0.1 and the variance to 0.1 also, and let's change this jitter breathe time to none. So like this should work perfect. So let's preview what we have here, and we can see that all of our particles are sourcing here. We have a nice noise, and yeah, this is really cool. I think maybe the whine is too high, and also as we can see, these particles are going down, and we don't really need these particles that go below our grid, because we won't be able to see this. So let's add here a pop kill like this, and let's activate this rule. And in front of this, let's say if our py is less than -0.1, which is below our grid, then that will equal to 1. Now also I forgot to change here the time scale, which is really important, so it's the same time scale as our original snow simulation. And let's also add here some gravity force. Now let's preview again. Now this is looking much better now, and as we can see here now on a few frames more, we will see that all of our particles will start to die. So yeah, as you can see here, they're turning in blue, and once they reach that 0.1 value, are starting to disappear, and this will save a lot of data and also will give us more performance on our simulation. So I think this is looking really good. This is looking really like a small snow, and the noise is really nice. So I think with this, we are ready to start baking. But as you know, and as I did a few times on this tutorial, we are going to compress these points a lot so we can save disk space. So let's start first by adding a attribute triangle, and I'm going to create my p-scale for later. So p-scale equals 0.0003, which is our p-scale from our snow value. And now let's start by compressing this simulation. So first of all, let's start by creating an attribute delete, and I want to delete everything, but I want to keep the p-scale, the v, and the h. Now let's promote our p-scale, so attribute promote, and we can promote our p-scale from points to detail. Now we can also cast some attributes, and I want to cast my velocities to 16-bit float. And finally, let's convert PDB points. Let's put this to 32 and change this to 8-bit fixed points. And now we are ready to bake. So let's drop a file cache, and as always, we can delete here the $s. We can save it on the folder we want. This is a simulation, so let's keep it like this. And I want to bake 120 frames. Okay, so now that we have our particles baked, we can do the same thing that we do always. So convert our PDB points, and we want to extract the points. Now we can attribute promote and promote our p-scale from detail to the points. And the next step here is to make our particles a VDB, because I want to render everything as a volume. So let's drop here a attribute create, and let's create here a density attribute, which I'm gonna give a value of 1 for now, but later we will tweak this, as I want some parts to have more density and other parts to have less density. And now, as you can see here, this shape is super big, and I don't really want this to have the same density all the way around. And what I mean with this is that I want this starting part to have more density, and then from this part to the end of the line, I want this to start going down on density. So maybe this part has a density of 1, maybe these parts have a density of 0.5. From here to here, I want it to go from 0.5 to 0. So to make this, let's create a attribute wrangle, and let's put that our density is multiply equal, and I want to fit my 8, and then let's add here a few values, so 0 to 0.1, and then 0.7, and maybe 1.2. So now here we have what I told you. So we have more density here on the center and then less density here, because we are multiplying this by the 8. So if I preview here the 8 attribute and I go here to 0.1 maybe, yeah, so it's the same value as here, 0 to 0.1, so 0 to 0.1. So we can see here that the values that has the 8 on 0, it's going to be less density, so 0.7, and then the values that has 0.1 will have 1.2 of density. And we can continue by rasterizing our attributes. So let's drop a volume rasterize attributes. And here let's rasterize the density attribute, and our box's size is 0.003 as we said earlier. Let's put this filter to points. And I also want to add the velocity blur for later on rendering to have a blur on our smoke. So let's put maybe, I don't really want a lot of blur. And then let's change also this coverage scale to 10. So now we can preview this. And yeah, as you can see here, we have our points converted to smoke. And as you can see here on the center, we have more density, and here we have way less. And maybe I want to change this value from the attribute create from 1 to 2. So we have a bit more of density. Maybe on the attribute triangle, I want less here. So maybe 0.6. Yeah, a bit less. It's not a really big change. And now here we can create a null and call this out snow extra, because this is our extra simulation. I want to put this on red, so I know this is the last node. And now let's go to the top again, and let's duplicate this blast from here to here. And now let's change this delete non-selected, so we have the opposite. Instead of the big chunks, we have this, and we are going to take these mesh chunks, which are animated. So let's object merge this here, and now we can create a group as we did before, and we're gonna do the same thing as we did here. So we're going to delete the points that are around this VDB. So let's just connect this here. Let's call our group delete, and then put keeping bounding regions. And instead of bounding box, let's put bounding volume. And here on the ISO surface, let's put 0.003. Oh, sorry, and we have to point this into points. And yeah, I think this ISO surface is okay, because 4 is a lot, and 2 is not really taking all these parts. So yeah, 3 is the good value. And with this, we can create a blast node and delete this delete group. So we are deleting all of these that we don't really need, and we have this extra snow. And now we're going to copy this attribute triangle from here to correct our velocities. So let's copy it here on the left. So we have our velocities correct, and we can also copy the attribute triangle from here, so the p scale, and let's connect this here. So we have also the p scale here, and we can do also some cleanup. So let's do attribute delete, and we got delete everything, and I want to keep the p scale and the velocities. And now let's go here below, and let's copy this attributes create. So let's copy it here and paste it here. We have these attributes create on the density, and I want this snow to have a bit more of density. So let's put 5 here, and we can also copy the same volume rasterize. So let's copy this from here to here. So we can rasterize this into a volume. And now let's create a null and call this out snow detail, for example. Now we can color this into red, and let's go back here up, and let's do the same thing, but this time with our big chunks. So we can put delete non-selected here. So we have our big chunks, and now let's copy the attribute triangle, the velocity, and the attribute triangle from the p scale. So these two, we can put this here. We can also copy the attribute delete here, and let's also copy this attribute create the density, and maybe I want this to have a bit more of density, so let's put a value of 7, and yeah, also copy this volume rasterize attributes, so we have this as a volume, and yeah, just create a null and call it out snow chunks, for example. Okay, so with this we finish everything. We have here our big chunks, we have here our detail, and here our extra snow simulation. So now we are ready to render this shot. For this last part of the tutorial, which will be the rendering and the compositing part, I will just do a quick walkthrough on the nodes and the things that I did on both render and compositing. And this will be a super quick and easy thing because I didn't want to spend a lot of time compositing and rendering. So I just started by importing all the objects like the helmet and the snow. Then I just create a material for the helmet, and then I create a material for the eyes also, which is an emissive material in blue color. Then I bring the snow, I just merge it, I create a material, which is a simple karma pyrosider. I just put the density on 5, shadow density on 0.3, smoke brightness on 3. I change a bit the color to be more towards the blue. And yeah, I think this is pretty much everything on the materials. Then I just merge this over. I just import my camera. I create a dome light with an HDRI. Then here on the render geometry settings on this first USD render drop, I just took out everything but the big part of the snow, so the chunks. So if I preview this for a second, you can see that I'm only rendering the big parts of the snow. Then on the second render geometry settings, I took out the helmet, the eyes, and the big chunks of the snow. So here I'm rendering the detailed snow simulation. As you can see here, I'm just rendering these small parts of the snow. And then on this last part, I just took out all the snow, and on this last render geometry settings I just took out all the snow simulation, so I can just render the helmet. And as you can see here, I'm just rendering the helmet with the eyes. And yeah, for the AOBs I just took all the combined diffuse, direct diffuse, indirect diffuse. For the reflection, combined glossy, direct glossy, and indirect glossy. And for the lights and emission, I took the combined emission, so I can take out the eyes on Nuke. And then on the snow effects, I didn't add any AOBs, so I just export the beauty. And here also, as you can see, I just export the beauty. And yeah, this is pretty much everything from the render part. Okay, so for the nuke part, here we have the helmet, then here we have the big chunks of the snow, and then here we have the extra layer of snow. So for the helmet, I just took the combined diffuse, glossy reflection, and the combined emission, then just merged them over. Then for the emission part, which is the eyes, I just color correct it a bit, and then add a bit of glow. Then here also I color corrected a bit the helmet, then merged everything over. I transferred the alphas because here I didn't have alphas, so I transferred them back. And then for the snow, I just transform it a bit up. And then for the extra layer, I used color corrected because I didn't like this red color that it had on the render. So I just gain it down, then merge this over, and merge this on the helmet. Then I just add a bit more of motion blur, color corrected a bit more again. Then I reformat this to 180p because it was 4K, so I put it into 180p. And then just write it into EXR sequence, so I can get aces on DaVinci Resolve and further compete there with some more color corrections and things that you will see now. And now for the DaVinci part, what I just did is to add a background with some blur effect here. Then I just add a few overlays like snow, some atmosphere, some more atmosphere here on top, a few more snowflakes, and then some color grading. And then to add a bit of life to the shot, I just add a few sound effects like this. And yeah, for the color correction, it's just a few curve adjusting, and then here I have some LUT that comes here on DaVinci Resolve. And then to finish with this, I just add a glow with this H versus B ratio in 1, so you can see that it generates these cool lines on the eyes. And yeah, this is pretty much everything from the compositing part. I hope you enjoyed this tutorial, and if you like it, let us know in the comments. As I said in the intro, we can bring more about MPM and more free cool tutorials to Bauxite. So yeah, hope you guys have a great day.